Welcome back. This video we're going to talk about ordinary differential equations once again, and more specifically we're going to look at what we call higher order methods. Basically we saw Euler's method as an example of a first order method derived based on the Taylor series just a video or two ago, and today we'll expand upon the idea, essentially try to take higher order terms in the Taylor series to derive slightly different methods such as the Midpoint Rule method and more general Runge-Kutta methods, and we'll also see how to call the MATLAB function. So, just to have a slight flashback, we began by understanding what ODEs are, why are we using ordinary differential equations, basically for modeling. We talked about initial value problems. We learned how to recognize ODE usage and systems of ODEs, identify the dependent and independent variables, and classify ODEs. We then also started looking at how to solve ODEs using the computer, numerical methods. We talked about Euler's methods, saw a few examples, talked about error in Euler's method, talked about multivariate ODEs and some MATLAB examples. And today we're going to see some higher order methods. So let's talk about the basic idea of what we have talked about so far and how we can improve upon this a little bit. So let's imagine that here is our solution curve. So let's say we have an ODE, which once again we stated as f prime. Maybe I'll use y prime here instead to match the figure. Let's say this is y prime of x will be equal to a function, some given function of the independent variable as well as the dependent variable, which we'll call y of x, right? Sometimes in the past we've used t for the independent variable. In this case here in this video we're using x. But in any case, we're given this, and we're also given the initial value, right? This is an initial value problem. So we're given some x naught, and we're given y at x naught, which we're calling y naught, right? So these are given. This is our initial value problem. And so there will be some curve, some solution, y of x, right? This is what we're seeking, the solution y of x, that satisfies both the left-hand side and the right-hand side of this equation. And let's pretend, just for the purposes of graphing this function, that the solution, the true curve, is given by what we call the solution curve, right? So that's what we're trying to find out. And basically what we did before was to take the Taylor series approximation at this point, at the starting point, and we took only the first term of the Taylor series, which leads us to approximate the solution curve with a line instead, with the line being the same derivative of this function. So let's write what we did in the past, right? We were looking for the Taylor series expansion, so we'll write Taylor series. For y at x naught plus h, that will be equal to y at x naught, which is given, plus h y prime x naught plus h squared over 2 y double prime of x naught plus higher order terms. And exactly as we discussed before, if we just take these guys, we call this Euler method, right? And this is essentially this curve as it's being drawn here, right? You can see as a function of h now, this is simply a line, right? And h is me stepping away from this, right? I make h big, for example, this size, then we're at x1. So we are going to find the solution point by point. So we start here, and our next point will be x1. And we can see that this x1 here is not exactly on the solution curve, so we're making an error, right? How can we improve upon this error? Well, one idea is to essentially take the remaining terms, right? We have more information to use here, right? And this is what we call, if we use this, we call higher order methods. So in essence, our method will still be driven by the Taylor series, and we'll still use an expansion that looks a little bit like the standard Euler method, right, where we have x plus h will be equal to y at x, and we're going to put some h and some phi value here, right? Or sometimes we may write this as y I plus 1 equals y at I plus h phi, right? The difference here is we're calling the explicit variable x, but of course we're solving this in the computer, so we're going to store this in arrays. We might as well index with an integer index, right? So the meaning is the same, it's just written slightly different. This is a little bit more programming friendly. But in any case, note that we're using this value phi here for this function. And essentially this value phi will be our way to approximate this Taylor series using, more terms. In addition to just the linear term, perhaps we also want to include a quadratic term. How would we do that? Well, in previous videos, we also saw how we can numerically differentiate a function. There are finite difference formulas for estimating the first derivative of a function. There are finite different formulas for estimating the second derivative of a function. So what we're going to do now is essentially take, other estimates. For example, we could use the estimate, of the derivative at this value, or we could use the estimate of the derivative of the function at this value, whatever it may be, as well as estimates of the derivative steps along the way. And basically, we can use finite differencing formulas to start approximating better and better the higher order terms that we need, right? And these methods that we're going to talk about are generally called Runge-Kutta methods, because that's where the idea comes from. So let's look at the first simple version of this idea. It's called the midpoint method, right? So, and it's a very hopefully simple idea to understand, right? So once again, we have our ODE. It's written this way, and we're going to estimate some phi here. But instead of using the I apologize, this should have had no, that's correct. It's correct. So. Right, instead of using the point at the beginning, note that we're calling I plus 1/2. What sense does that make? Right, so let's explain. So let's go back to the standard Euler method, right? So if I chose the phi here to be this slope, right, which is given by dy dx at x naught, that's what we would have used, right? We would have plugged in here f at xi yi. This is this regular Euler method, right? But note that we are not going to, we don't want to do that, because this slope here, if I take this step, I'm going to end up here, and that's an error. We want to end up somewhere closer to here. So you can see I could choose this slope instead. I could choose this slope instead. I could choose the slope at any points of this. And for example, had I chosen this particular slope, right, I would end up way off, maybe way up here. So there may be a slope somewhere in the middle, for example, some slope at around this midpoint here, that if I take this step, I'm going to end up a lot closer to the point that I want. So that's exactly the midpoint rule. So what do? We first estimate y at x plus, let's say, xi plus h over 2. This is what we're calling that, right? We need to estimate. Of course, we don't have the value of that, but we can estimate that using the regular Euler's method. Once we have the estimate for this value, which is, we're trying to get the estimate for this midpoint slope, right? Because if we use this midpoint slope, we're going to end up closer to the actual value we want. So we can estimate what that would be. We'll make an error with that. But once we have this, right, the xi plus h over 2 and the corresponding y at xi plus h over 2, then we plug it into our function to obtain the right slope, right? And this will be our phi, right? And this is what we're plugging in here, and that's what we call the Euler's method, midpoint method, or improved version of the Euler's method, right? And then you can say, well, why stop there? Why can't we take an average of many points of this curve along here and estimate an even better slope that we can take a step to end up even closer to here? And that's the general idea of what we call the Runge-Kutta type methods. The most famous of which is the Runge-Kutta order 4 type method. And it's a very similar idea. So now we're going to use the same formula at the beginning, right? But now our phi here will be different. What is our phi? Our phi essentially will be an average of 4 k's, right? It's a weighted average. So this weighted average looks a little bit like some of those finite differencing filters, right, that we talked about, or our finite difference derivative estimation equation that we talked about a few lectures ago, right? So we're going to, and what are the values of this K1, K2, and K3, and K4? So K1 is the value of the slope from the initial point, essentially. It will be, Euler's method, right? K2 will be the same as the midpoint method, right? So we can take K1 here and estimate Euler step, right? This is the Euler, the step using Euler's method. And then, this, we can call this guy the midpoint slope. Right? And so that's K2. We can also take K3, right? So for example, we already found out that K2 may be a better estimate for the slope that I need to use starting at x naught, right? So by the way, note that here we went back to time as the independent variable. But we already found out that K2 may be a better slope for me to use starting from K0. So I can use K2 at for my new estimate of this half-point step, right? So this is kind of like, you can call this the improved midpoint method, right? It's one way to think about it. And then you can use this K3, which is our improved midpoint method, to estimate the value of the function at the full step, right? And that will be even a better slope, right? And in fact, this combination of K1, K2, K3, K4 can be used sort of in a derivative finite difference approximation to come up with this formula. And if you use this, this will be a fourth order method, right? So taking many terms of the Taylor series, not just the first order term, right? And this tends to give you a very good approximation to the solution of the ODEs that you may have. So how do we do this in MATLAB? Here is the syntax for the famous MATLAB function. It's called ODE 4.5. We'll explain 4.5 in a second in a subsequent video. But for now, let's just look at what these are, right? So this is the t here will be our independent variable. Of course, in MATLAB, you can call whatever, you can substitute this here for x, whatever you would like. I'm just using some variables here that we can talk about. This will be our dependent variable, right? If you want to call it z, this is no problem. And these will be the outputs of this ODE 4.5 function. And here, right, so this guy here will be our MATLAB solver. And this guy here will be the function name for our ODE function. Right, essentially this will be the name for whatever function I need to use to compute this guy. Right, so first of all, we're going to talk about how to, given a more general ordinary differential equation, we're going to talk about how to estimate, how to transfer this Runge-Kutta, the whatever ODE you're given into this form, right? And once you do, you can use this function. So this t-span here will be the range, for let's say call it t-min and t-max, meaning what is the range of the time variables that you would like to solve for, and this is going to be your initial value, right? So this is an initial value problem solver. And this is one of the famous workhorse functions in MATLAB that we're going to use it in a subsequent video to solve a sample ODE problem.